Hey guys, I hope you're all excited for excitation tables. I try to make these funny, but it never works. It's honestly, it's super dry material, so I apologize. I do my best. Alright, well, let's get started. We're going to do a problem where we are given a value e and a value x, and these are inputs into some kind of circuit that requires JK flip-flops. So we're only going to be covering the excitation table part of this question, so we won't actually get to the JK flip-flops. But if I think I have enough time, I can explain how to get there. So we have a few conditions here in the question. It says that when our input E is equal to 0, that there will be no change in our output. So that means whatever goes in comes out the exact same. And let's see, when E is equal to 1 and X is equal to 1, then we will have an up counter. So that's from 0, 0 to 0, 1 to 1, 0 to 1, 1. And when E is 1 but X is equal to 0, we have a down counter. So that means that we go from like 0, 0 to 1, 1 to 1, 0 to 0, 1 and so on, and it just loops around. Here, we don't need to worry about that because there's no change, right? So, let's look at just a counter in general. Let's take an up counter. So you start at 0, 0, you go to 0, 1, 1, 0, 1, 1, and then it just loops through. So it keeps going and going and going. So I think we can all agree that 4 things happen in this question. We start at 0, 0, and then something happens, and we go to 0, 1, something happens, we go to 1, 0, something happens, we go to 1, 1. So when 4 things change or when 4 things happen, that means that we have 4 states. Okay, so that means that we are going to have 4 things happen in our excitation table depending on E of x. Now within these 4 states, E of x can be 4 different things. So let's split up our states into 2 values, A and B. So here, when A and B are 0, 0, E and x can also be 4 things. So E of x can be just going up the truth table here, 0, 0, 0, 1, E and x. So now we want to make 4 of these, so I'm going to cut out for a second and just finish up the table. Okay, so this is our table. I've just completed it. So again, this first one, that's state 1, state 2, state 3, and state 4. Okay, and in each one, E of x can be its 4 different values just going through the truth table, starting at 0, 0. So when we have stuff with flip-flops, we're always looking at present states and next states because we are also dealing with a clock, so this value changes with time. We have different pulses that occur at different times. So what we're doing here is we're really looking into the future. We want to see what our next A and what our next B will be. So those little signs beside the A and B are just plus signs. So that means that here we will have our present state, and here we will have our next state. So these will change depending on E and X. So we look at our little kind of legend here, and we say that, oh, okay, well when E is 0, well, A and B aren't going to change, our counter's not going to change. So if we look here, we can actually see that, well, you know what, I'm only going to highlight E. E is 0 here, E is 0 here, here and here, here and here, and here and here. So in these spots, our values just aren't going to change at all. So that means that our next state for when E is 0 will just be 0, 0, because that's the same as here. And then it's the same thing below, so that's just going to be 0, 0. This is going to be 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Okay, so next you look at when E is 1. Alright, so in these cases something's actually going to happen. So when E is 1 and X is 1, we have to count up. So we look at when E is 1, oh, E is 1 here and X is 1 here. So we have to count up from our A and B. So that means that here we're going to have 0, 1. Okay, now we look for E where E is 1 and X is 1 again. Here it is. Oh, we have to count up. So that's 1, 0. And then here, E is 1 and X is 1, so we have to count up again. That's 1, 1. Here E is 1 and X is 1. Oh, but we're already at the top here. We're already at 1, 1, so where do we go? We loop back through. So now we're just going back to 0, 0. Alright, so now we're going to look at our last case where E is 1 and X is 0. So we're counting down. So it's the same thing. Here we're at A and B, but that's the bottom, so we have to loop back around to 1 and 1. Okay, so here we're counting down, so we're going down to 0, 0 again. Here we're counting down, so we can go to 0, 1. Here we're counting down, so we're going down to 1, 0. Alright, now this problem uses JK flip-flops. So we have to figure out what we need to do within the JK flip-flop to change whatever A and B is in our present state to whatever it is in the next state. So we split up our counter variables again. So remember doing A and B. So our two flip-flops will handle A and B separately. So that means that we'll have kind of like a JK flip-flop that deals with A and a JK flip-flop that deals with B. Okay. Now we have to remember what our JK flip-flops do. So we'll just do this down here. We got J, we got K, and then we got Q, so that's the next state. When J and K are 0 and 0, when it's 0, 1, that's 1, 0, when it's 1, 1. Oh god, everything's going wrong. No change. So when J and K are both 0, there's no change to the next state. Here, Q will just be 0, here it'll be 1, and then here it will toggle. Alright, so let's start with our A value. So we want to get A from 0 to 0 using our JK flip-flop. So now we look at our truth table again, and we say, okay, well, 0 happens here, and 0 happens here because we're not changing anything, right? We're going from 0 to 0. So that means that J has to be 0 all the time, or else we'll end up with some other variables. And K can be either 0 or 1, it doesn't matter. So that means that here, JA will be 0, and KA is a don't care, because it can be either 0 or it can be 1. So now we do the same thing here, because we're just going from 0 from 0 to 0, sorry, for A. But here now we're going from 0 to 1. So now we look at our truth table again. We want to change our 0 to 1. How do we do that? Well, here our output for our JK flip-flop will be 1 all the time. So we like that case. And since we're going from 0 to 1, that's just a direct flip. That's just inversing. So that means that we can take the toggle as well. So J here always has to be 1. But then K can either be 0 or 1. so we have a don't care. Now here, going from 0 to 0 again, so that's just 0D. So now let's look at the JB side. So we're going from 0 to 0, so we know that's 0D. 0 to 0, we know that's 0D. And here we're going from 0 to 1, so we know that that is 1D. And then here we're going from 0 to 1 again, so we know that that is also 1D. So that's the gist of it. I'm not going to really fill out the rest of this. It should be a good exercise to figure it out, but I've explained everything, I think. So what I want to do now is just briefly explain how to turn this into a circuit. Where's my pen? There it is. I don't know why I scrolled down. Okay, so we have kind of 4 results we want to look at. We have JA, we have KA, got JB, and KB. So what happens next is, since an excitation table is really just an overglorified truth table, we have JA do the K-map of that, KA do the K-map of that, JB do the K-map of that, and KB do the K-map of that. So what happens when you do the K-map afterwards is you have simplified equations. So I know that for JA, you'll end up with something like this. E and then B exclusive or X inverted. So that means that your J value that will plug in to your flip-flop that deals with A will be this equation. I'll go into J and then I'll do stuff and come back out. So you're doing that for each one of your flip-flops. So I think that's it. Feel free to suggest ideas for new videos. Finals are coming up soon, so I'm probably going to have a huge wave of videos coming out at that point. But I suppose till then it'll be pretty quiet. So thanks for watching. Subscribe if you want. I'll be making videos all throughout my computer science degree, hopefully, because it helps me probably just as much as it helps you. Thanks again for watching, and I'll see you around.